Have you ever wanted to recreate Michelin fine dining cooking at your home? You brought these high-end raw fish and cooked them, just to end up with diarrhea the following day? Well, we just have the solution for you. Take Cornell's 3500 Heat and Mass Transfer with Professor Data, and you will learn everything.
Take heat and mass indeed. And as current students, let us tell you the best way to model cooking time for tuna steaks of different sizes. We're going to start by defrosting our fish in a cold bath of water. Dry them and cut them into our wanted geometry. We'll cut the first block of tuna into strips and then into smaller cubes. We start with cooking the cube. And got an average cooking time of 3 minutes and 36 seconds. We then move on to cooking the rectangle steak. Getting an average cooking time of 13 minutes and 20 seconds. Finally, we cook the slab steak. Getting an average cooking time of 60 minutes and 16 seconds.
Our experiment mainly consists of heating up the yellowfin tuna fillet and interpreting this in transient heat conduction model using different dimensionality of 1D, 2D, 3D to see which geometry best represents each model, and finally determine which geometry will take the most amount of time to heat up. On the slides is the schematic, the simplified diagram for each slab, rectangle, and cube. There is the boundary condition and each dimension listed on the slides. These are the governing equation and boundary condition as well as the initial condition listed in order to solve this problem. For this problem, we assumed no heat generation and no bulk flow, resulting in the time term and the three-dimensional terms. We also pasted in the flow chart from the back of the book, and we decided that we'll be using an unsteady conduction problem with finite geometry and one-term Heisler chart using superposition for two-dimensional and three-dimensional analysis. Now is the solution. Below is the assumptions made for a tuna, and we also lumped the conduction and convection in the pan, as well as natural convection and hot air and minor radiation into one single H effective value. And to find the H effective value, we use the characteristic length of 0.025 and air properties at approximately 70 degrees around the tuna as the pan is heated. Therefore, we use K value of 0.03, Prandtl number of 0.7, and with the laminar and natural convection from the pan, Nusselt number was 7. Therefore, we estimated the H effective value as 10. We calculated the dimensionless time, which was 0.786 for central temperature of 50 degrees, and we calculated the Biot number for confirmation of Heisler chart. We also found the Fourier number for each dimension. Essentially, we calculated the Fourier number for all three geometries, where slab had the z-dominating behavior, while rectangle behaved 2D in the xz plane, as only y-axis could be negligible, and while cube behaved like 3D because it had the same characteristic length for all XYZ plane. We finally calculated the time it takes to cook the tuna for all geometries, and as the calculation suggests on the slide, it says the slab takes the most amount of time, followed by rectangle, then the cube.